Semiconductors and Mossad Labs is founded by three people. Mr. Rajesh Gupta, who has about 27 years in industry experience. So last 13 years, he was the country head of two global competency centers. He was the country head of Micron, Bangalore, and also country head of AMS Osram. A person with 25 plus patents and has he did his BTech from IIT Madras, All India rank 127, did masters from USA, and very strong industry veteran in this. So developed several semiconductor IPs that went into a lot of very chips, automotive products, and so on. About me, I'm Dr. Krishnakant Tavalur. I have about 23 years of industry experience, and I was previously the director of analog mixed signal R&D in the AMS Osram. I have about 13 patents, 10 IEEE publications. I'm also the adjunct professor at IIT Hyderabad and the State University Kerala. I'm the associate editor for transactional circuit systems, express briefs as well. I did my BTech and MTech from IIT Bombay, passed out in 2002 with a President Gold Medal from IIT Bombay, and then while working in industry, also did my PhD from IIIT Hyderabad. I worked with Texas Instruments Bangalore, then Qualcomm Logic, and last 19 years with AMS Osram. So I've designed several automotive products, automotive sensors, airbag deployment sensors, reverse camera sensors, system-based chips, and the last 9 years we've designed several optical sensors that went into Apple iPhones, Samsung phones, and the latest one is a temperature sensor. It's the world's smallest and most accurate temperature sensor that went into iWatch. Apple iWatch. And the third person is Mr. Madhusudan Sampath. He has about 25 years of industry experience, and last he was the director of system on chip and system. His team has designed he was leading a team of 160 engineers in Samsung who designed the Exynos processor. So if you're using a Samsung A series mobile phone, A55, A57, the processor is designed in India by Madhusudan Sampath and his team. Madhusudan has MS in Applied Electronics from RSA Trichy and a PG diploma in VLSI from CTAC. So,
our industry, fortunate enough to have such intellectuals amongst us. Thank you, sir.
Thank you, our pleasure. So, what do we do? So, we have two companies, or you can say two initiatives. First one is a product R&D, which is called Mossad Semiconductors. And we are building India's first indigenous battery management system on chip. In fact, this will be world's first BMS single chip solution with electrochemical evidence spectroscopy. This is primarily targeting electric two-wheelers, three-wheelers, garden tools, and the four-wheeler market. This will be a world-class chip, but will also help India to be self-reliant and cut that Chinese ecosystem. Right now we are flooded with Chinese BMS, and this will be first built in India with a much better quality, fantastic features, and very price competitive compared to the Chinese designs. That we are doing as part of Mossad Semiconductors, and then as part of Mossad Labs, which is a VLSI EduTech initiative, we are working with several universities and also with governments to focus on building semiconductor workforce in the country. So essentially, the course is designed by industry leaders, and we focus on learn by doing. And I will talk about more about these programs soon. Let me give you a quick glimpse of what we do as part of Mossad Semiconductors. So we are building the single chip battery management with inline EIS. What does this mean? If I show this in one slide. Today, if you look at every battery pack, this battery pack, lithium-ion battery pack, and the problems right now is that the state of charge, which is the fuel gauge of the battery pack, can be incorrect if one of the cells, one of the lithium-ion cells go bad, and there is no way to monitor each cell inline on a regular basis. Typically, this is done in a service station once in 6 months. When you take your EV to a service station, they'll check your battery and then say whether the battery can go for next 6 months or not. But it's very possible that, and we have seen many cases in the past that that one of the cells go bad and then suddenly the state of charge the mileage suddenly drops down from, let's say, 100 kilometers to 10 kilometers, right, on a highway. Very bad. Second thing is that's mainly because there is no predictive health monitoring. Okay, so when the state of health of the battery goes less than 80%, you are asked to replace the battery. It just means that today there is no reliable way to understand when exactly the failure will happen. And third, it's very easy to sell a petrol vehicle, but whereas if you have a 5-year-old EV, there is literally no second sales market. Basically, it's sold as a scrap because there is no way to measure the health of the battery. And this is exactly what this chip will solve. It's a battery management system on chip with inline electrochemical impedance spectroscopy. EIS is like a ECG for a battery. It will detect exactly how the health of the battery is, every single cell, and will give you the predictive health and reliable second sales market. Okay. So that's what we are building right now. We of course want to also hire analog design engineers in our company. So primarily we are a semiconductors company, which is also doing this EduTech initiative. Right? Okay, so about VLSI design and process loop, quickly going to this. Now, before I talk about VLSI, it's a known thing that future is clearly the semiconductors, and if that future is now, we know that our honorable Prime Minister is talking about semiconductors, and there are global giants like Tata who are also investing heavily into semiconductor manufacturing. Minister Ashwini Vaishnav is talking about having India in top 5 global manufacturing destination semiconductors. And many articles you see in press these days that there's a demand for 40,000 to 50,000 new VLSI engineers every year. So there's almost 20-30% increase. Why is this? Because semiconductors has a national asset. Because future wars will not be fought on the battlefield, but they'll be fought on algorithms, they'll be fought on semiconductors, and they'll be fought on supply chain. So very important for the country to be self-reliant in this. And one of the fantastic things about India is that 1/5 of the global world VLSI engineers are from India. Okay, so and we need to leverage that. Of course, we still are taking initial steps in manufacturing and supply chain, but we need to leverage our strength here and then build a world-class design pool inside our country. So if you look at the semiconductor value chain on the left side, there are 2 models. One is the fabless model, which means the companies that own the IP, but they don't manufacture. They manufacture it in the foundries. As an example, AMD, NVIDIA, Broadcom, the biggest of the players, they build the design like NVIDIA, it designs the GPUs, but gets it manufactured into a foundry like a TSMC or a Samsung. It is also tested by Teradyne, Advantest, or packaged also. Then there is a second model, which is an integrated model, where the design and the manufacturing also happens in the same company. Example, Micron, Samsung, Texas Instruments, Intel, Infineon, all of these are examples. And then you have a whole layer of supply chain in between, where we talk about design software, R&D tools coming from several vendors like Synopsys, Cadence, Siemens, etc. And of course, supported by the manufacturing, assembly equipment, and the raw materials. This is where China really dominates the supply layer that is supplying the infrastructure for the fabless and integrated model. And as a fun fact, if you look at the semiconductor supply chain journey, an IC, a chip that gets designed somewhere, travels about 25,000 miles across 80 to 90 borders, in different phases: design, fabrication, wafer production, sorting, testing, packaging, assembly, and then all supported by all the raw materials and everything, right? Distribution. So if you look at it, it's such an extremely complex supply chain, and this is the reason why semiconductors as an industry is a real deep tech foundational industry. So unlike a conventional software app, right, where you can probably sit in a room and build an app, it's very easy to kind of build an app completely. But designing semiconductors involves, you can't sit in the room and design a chip. That's the thing. That's the point. So that's why semiconductors is a foundational industry, like steel industry, right? So steel is everywhere. Similarly, semiconductors are everywhere, and hence it needs a certain amount of knowledge and understanding of the entire supply chain, different parts of how things come together, and that needs to be incorporated well into design phase. Okay. So with this, I would like to know all the students who are trying to pursue VLSI or want to understand it. I want to tell all of them that VLSI is a core branch. Absolutely. Why? There is growing demand for VLSI. India VLSI market is expected to be 110 billion US dollars by 2030. Very, very extremely lucrative business. And VLSI is a domain in itself. You would have seen that starting 2022, our government has introduced VLSI as a discipline. BTech in VLSI have started in the country. VLSI has its own specializations now, like in CMOS technology, analog design, digital design specialization, where trained engineers in this are really building experts and becoming experts and building products in this niche area. Fantastic career opportunities. Starting salaries in this are 10 lakh plus, and if you're 10 years or more experienced, then the salaries go to about 50 lakhs to 1 crore. And after 10 years, right, you're returning in global demand, because there's always this worldwide shortage of VLSI engineers. So once you get to a 10 years experience, you have a fantastic career there, and your salaries are much higher. And if you're 20 years beyond, you're really making a lot of money there. Right? And why does this growth happen? This, if you look at an average software engineer salary versus VLSI engineer, the reason why VLSI engineers career growth is exponential is because when they spend a few years in industry, they will see the entire cycle starting from design to manufacturing, testability, production, ramp up, and there is learnings in the entire every phase. There is a certain amount of learning, and that experience, that continuous learning of building products is what goes into the design. Like when they start doing a next IC, they start with a much more enhanced idea of building the products and making a fail-safe designs, right? That learning is what really catapults them to a fantastic career there. Now in India, we also have it's a great time to think of your own hardware startups, right, in India. Last but not least, VLSI is really the future. And if you think of the biggest gainer of this AI revolution, which is NVIDIA, NVIDIA is a VLSI company. It's not an AI company, right? NVIDIA makes GPUs that enable all these LLM models to be filled in. It enables faster compute. It enables all these edge AI applications, all the hardware that we are able to build today. So VLSI is literally the backbone of AI. And the reason why, even though AI as a concept was thought of in 1950, AI has become mainstream only in the last 5-6 years. And I think as we speak, we have the largest AI conference happening in Delhi right now. And hardware is a big part of this AI. So any new technology like medical, robotics, EVs, wearables have to rely on VLSI. And that's why it's very important to build a fantastic workforce in the semiconductors in VLSI. Okay. So just for some curiosity, you may see that the first computer that was invented in 1946 was the size of 3 BHK flat, weighing 27 tons. And 75 years later, we are talking about an entire wafer being one single chip with 1.2 trillion transistors, right? And what you could do in a 3 BHK flat size is now possible in a very, very tiny chip, the same amount of compute and miniaturization. So that's the beauty of how far we have come through this semiconductor revolution. Okay, so little bit about what are the career options for students who want to join the VLSI industry. First is clearly the analog design. So most people, we know that digital is literally the rock star, right? Everywhere we hear about digital bit stream, and most faculty students know about digital more. They find it a lot easier. But keep in mind, anything that interacts with the real world has to have an analog content. So without analog content, there is no human-machine interaction. Right? So as an example, if I ask you what is the temperature of this room, right, or the room that you are in, you will not say the temperature of the room is 10000011, right? You will say that it is 25 degrees or 30 degrees centigrade. So any real world signaling is analog in nature, but these analog signals are prone to interference, and hence digital, once you convert into a bit stream of zeros and ones, you can do fantastic signal processing encryption. That's why digital has become very, very popular. Then the third one is called radio frequency design. This is the high frequency analog. Essentially, all the 4G, 5G, 6G, high-speed serial deserializers, all of this are coming in this very niche radio frequency IC design part. Fourth, embedded students usually know this. So this is using a software on an existing hardware design to control. Because somebody is giving you, somebody has already designed the controller, somebody has designed a microprocessor, or somebody has designed an FPGA for you. You are now building a software code and dumping onto that to use to make some useful functions out of this. So it's a software employed on a hardware for a meaningful thing. So it's still not VLSI because you are not designing the microprocessor, you are not designing FPGA or a controller. You are only using the FPGA as a proof of concept. So these embedded is nice for a quick proof of concept on something, but ultimately if you have to put it in a product, it has to come in an ASIC manner, which means you have to custom design the analog digital IPs in a single chip. Fifth is memory, very important topic where memory talks about data storage, retention, and retrieval. We all make our choice of purchases based on how much memory we have, how much memory my laptop has, how much memory my phone has, because we're generating so much of data, 4K, UHD, cameras, YouTube videos, camera videos, and all of this needs to be stored. Right? That's why the memory companies have really blossomed. Sixth is EDA. EDA stands for Electronic Design and Automation. So every transistor, the transistor fabrication is basically a chemical process. Right? And you need a way to map this process and the properties into your simulation system environment so that you can now use them, connect them, simulate them together to predict how the outcome is going to be. And this is quite powerful. And this is the reason why we're able to, while the entire manufacturing or transistor building is now brought into our computer using this model. Okay, so all the tools that you use like Cadence, Synopsys, all these EDA tools fall in this category. Next is testing and validation. The test, semiconductor testing is an absolute deep tech business because considering the hundreds of millions of components, the IoT, the mobile phones that are getting produced, and each phone carrying tens of different ICs and each IC having millions of transistors. Imagine the complexity of one application. So a manual testing process is absolutely not at all possible here. So it's completely automated way, based DFT characterization across electrical, thermal, optical properties, automated test equipment that is able to test these ICs in in the matter of seconds, milliseconds to seconds, right? So it's a very, very fantastic area there. And last but not the least, production, reliability, failure analysis, ESD, EMC, and yield. All these are important career options, and every chip that is designed in a company will have all of these skill sets that are necessary to do a chip. Okay, so if I look at what enables us to do, this is a CMOS technology. You would have learned in your coursework. You have an NMOS transistor and a PMOS transistor. If you slice it and then look at the whole technology recipe option, you will see that you're building an NMOS, source, drain, and gate, and a PMOS transistor with built in an N-well. And think of it like a ground floor where you have all the transistors in the ground floor. And you have first floor, which is metal 1. Second floor, it is metal 2, metal 3, and so on. Right? It's like a construction of a building, and you have vias that are connecting each floor to like a staircase. It's connecting the ground floor to first floor and so on. Like a house, unlike a house, right? The entry and exit for a house is always in the ground floor, whereas an entry and exit to a chip is in the top floor. So you have these bond pads of a top metal, which gets connected to an external pins, and that is where you supply your signal outside. So on the digital design flow, you start with many abstractions. So this means you start with the system level design. You look into the algorithm, what you want to build. As an example, you want to build a RISC-V processor, or you want to build, or you want to do an accelerator, right, or an emulator. You go through a system level design. Think of modules, how you will design it. You need multipliers, you need adder, you need combination logic. Then once you dig deeper into it, basically it has a combination of gates, and as you dig deeper into it, it's basically a circuit that comes behind, which has certain drive strength, certain fan in and fan out, able to drive a load. And then the deeper, the innermost layer is finally the device, right? So even a digital designer, has to finally map this design into a manufacturing format. This is where RTL to synthesis, and then using your place and route, static timing analysis, all of this comes into play. Ultimately, even with the digital design flow, you have to make a hard macro. Even with your code, you translate it to a hard macro, which can be sent to a fab for manufacturing. Analog design flow is similar. You do a block level design first. So as an example, you are looking into, let's say you use op-amps or comparator, passive components, and think of a high-level application that you're trying to build. Once you're satisfied with the outcome, you build these individual components, op-amps or ADC, whatever those blocks are. So you do a component level design there using all the transistors, then you simulate it, you verify it, and once your simulations are convinced with the simulations across all process corners, supply voltage corners, temperature corners, then you do a custom layout, which means you lay out transistor by transistor, all the different layers, you connect them, and you make a analog macro, right? So this analog macro and digital macro sits together in a chip. They are connected. You put your pads, power supply pads, easy structure, and ultimately you make an IC. So you start with your design on a computer. You make your GDS, which is a representation of how you manufacture, how you transfer the database to a manufacturing unit, and that manufacturing unit builds a photomask. Each layer has a mask. That mask is used to imprint your design onto a wafer. Once all the masks are used and you make the entire wafer with the transistors, you package it. This is the ASIC fabrication. And once this package is now put on a PCB, you write an appropriate software to talk to this, add all the other components, build the connectors, write the software that you can control this. And if you think that is all working, then you make an application node. This is typically like a smartphone or an IoT or an iWatch, right? So that's the usual cycle of a VLSI, and that is how you get your integrated circuit. So basically, this is your die where the top floor is now connected to the external pins using these tiny bond wires that you see here. Okay, it's just as a recap, because sometimes I feel that students get confused between different disciplines, right? So PCB design essentially means you are designing the green board on which the different components are getting connected. You do a schematic capture, place the components, solder it, you have appropriate routing traces and isolation, and you send it for manufacturing. Embedded system design essentially means that now you select a certain hardware which is already existing, like either microcontroller or as an example, Raspberry Pi is a classic example of an embedded systems design, okay, or an Arduino board. So you develop firmware, you write some drivers, do system level debugging, and finally you focus on integrating hardware and software for a specific function. The third set is an FPGA design, essentially more a reconfigurable logic, a very powerful prototype. Let's say you want to design and you want to, writing an RTL, you want to know whether your RTL core or your digital core is working. So instead of manufacturing it, waiting for 6 months and going through a fab, you can use an FPGA, port the code into an FPGA, and then measure the outputs so that you should be able to see how the code is working. Right? Remember, FPGA design, FPGA is still not VLSI because you are not designing it. You are using this to check your code, right? And as an example, if you have to design a pacemaker, it's a tiny chip. You can't put your FPGA inside your body, right? It's too big. So you really need to go to ASIC model, which is where you have the digital ASIC design and the analog IC design as the ultimate, right? So this is what this part of digital IC design and analog IC design is what we believe are the most niche areas which the companies focus on today. All the companies, they build their own ASICs which go into the product, and this is what we define from industry as a VLSI design. Okay, so next important question for the students is how do you build a successful VLSI career, right? So first, let's look at a semiconductor any chip design company needs in terms of building a chip. So the list is pretty large. Like I said, the supply chain starting from a requirement all the way till production and yield need several skill sets, and some of which we in India we are very popular from the product architects, the analog design engineers, digital design engineers, PD, validation, production tests. So all of these are the skill sets that you need in every chip company. So this is the jobs that people typically hire the students for. Of course, product development companies also need other skills like package engineer, quality engineer, reliability engineer. And every IC, you need all of these skill sets. It's typically a cumulative hard work of 50 to 1,000 highly skilled VLSI engineers. So it's not like, sit in a room and then you sit with a laptop and code it and somehow you're able to build an app. This is a hard work of tens and hundreds of skilled VLSI engineers over several years to bring you one single IP. And by the way, the latest GPU from NVIDIA has about 210 billion transistors. Right? Imagine how complex it is to design, connect, verify, manufacture all of these transistors. So that's the scale and that's the complexity I'm talking about when I refer to a VLSI chip. Okay, so a very relevant question. Let's look at what is the typical career path that we've been seeing in EEE and ECE. Before I talk about it, let's look at what computer science students are doing. Right? They study 4 years of computer science, algorithms, and so on. And obviously, they want to move into a job. For them, the software job is their core because this is what they've been studying. If we apply the same logic for EEE and ECE students, they study 4 years of electronics. And now you want to look at the core jobs for them. Obviously, the student is a bit confused. Okay, my seniors have not got it. My super seniors have now got it. Now, how am I going to get a core job? And then after 4 years, there is family pressure, friends, peer pressure, all of this. Right? So to find a job to settle down, naturally, the tendency would be to learn something real quick and then go and join an IT job. Right? And this is the process that you get. Nothing wrong with it. You're also joined by other friends in other departments because they face the same trouble. They don't have core jobs. So eventually, this is the route. So this is absolutely fine because, until about 5 years back, the IT and software industry had the volume of jobs that could absorb the number of engineers that become, right? But what has happened of late is the software industry has really got with AI and automation completely swallowing the entry-level jobs, right? And this means that CSE students themselves would struggle to find an IT or software job after studying for 4 years. So it's going to be even more difficult for ECE and EEE students or any other students to just look for an entry-level job somewhere to settle down. Right? And I also need to remind the students that about 40 years back, people who did electronics or electrical engineering always wanted to pursue masters. Many people who used to kind of pursue masters at that point of time. But once this IT revolution came in, then it became a default norm that I do 4 years, and then eventually even a fundamental field like electronics, we expect jobs directly after 4 years. And that's where really the problem or the mismatch in skill set comes from. Right? Okay, so I would say that the core jobs for electronic people exist, right? But we really need to bridge the gap. So we keep talking about industry academia gap everywhere in every forum across the country. So my take on this is I can summarize this in one line. See, the way we all learned in our textbooks, right, is how things work. You connect a set of transistors, you follow this flow, give this input, connect the power supply, and this is the output you expect. Right? So this is how, but this is usually the best case design. And even the most experienced engineer, when they start designing for the first time, right, things will never work. Right? So the ability to understand why things do not work, that part is missing. Because our textbooks will not teach you this. Textbook will not teach you why things are not working, why things won't work, why things will fail. And how do you debug things when things are not working, right? This is the part that textbooks won't teach you. And this is where the industry works day in and day out. Because when you are trying to innovate something, come up with a world-class product, things don't work on day one. So the ability to understand why things are not working and to make them work, right? Debug and make them work. That is the skill set that is missing. Okay.
And
And
how practically the things get happen.
sorry,
That
what was the question?
no, I was not questioning, sir. I was just saying that how practically the things can happen. This shows.
Yeah. So, see this gap, right? And see, one of the things that we also need to understand is where is the forum, where are the forums for the students to understand why things are not working? Every course has a lab, right? So, this is where the students also need to experiment a bit. So, they need to learn why things are not working. So, if they take their lab work seriously, then that's their first introduction into why things don't work. Because normally, I've seen many universities, and I'm part of board of studies of several universities here. We see that the labs are kind of more a formality that you have a fixed set of experiments that the student needs to do. They somehow manage to finish it, but whether how much they have learned is a different question. But the practical aspects. See, if a student struggled a bit and then maybe figured out why it was not working, right? That learning will stay with him or her forever. And that is where the learn by doing is what something that we need to focus on right now. So that's because when they join industry, there won't be textbook solutions there. So which is the reason why from our side, we try to focus on these aspects, why things do not work. And the other thing is when they want to join a VLSI industry, the jobs that they get, the job titles won't be electrical engineer or electronics engineer, right? It will be analog design engineer, digital design engineer, DV. So they already expect some introduction or some awareness about a specific field where they are applying for. So that's basically the two things that I want to get your attention on to. Now, the question is, how do you get these specialized skills? Now, we take an example of a medical field. I just bring this medical field analogy for explanation. So we would have seen that people who join medical industry or students who study medical industry, they don't look at joining a hospital after their 5 years, right? So every person who gets into MBBS, they study their 5 years course, 4 years of work, 1 year of residency, and then they want to specialize in something. Okay. And unfortunately, on the IT side, we think that 4 years of that breadth, whatever we learn, that's enough to get into a core industry like VLSI. And the difference between an MBBS doctor and a specialized doctor is that MBBS doctor looks at the whole system from outside. He's able to connect the organs. He'll say, okay, this medicine will work for that and so on. But only a specialist will be able to operate inside of the vital organ because there is zero margin for error there. Same rule applies for VLSI. VLSI is a deep tech industry where there is zero margin for error. The chips that are designed are extremely complex. There is no scope for any failure. The student or whoever is the designer of the chip, they need to understand in and out of the IC. Right? They need to know design circuitry inside the silicon chip with advanced EDA tools, not just use some ICs outside, connect the chips on board, solder it, write some firmware in the tool. Right? That still is needed in some cases, but the real niche is in miniaturizing it and building it in a chip. Okay. And this we believe needs a deep expertise and some specialization skill to be able to do this. And that's where we strongly focus on learn by doing, because once they design something, once they are able to do something on their own, then they can project their value to the industry or hiring managers in a much stronger way. Because like a medical school and hospital where the practicing surgeons are the teachers, we have come up with a program where the industry experts from different industries are the instructors who can give the practical application driven design knowledge. So So by no means this is not a replacement for a university education, no, because they need to know the theoretical background, they have to know the fundamentals. Absolutely, that process is necessary, but this is an additional thing to bridge the gap between what industry wants versus what the current students learn. So, question is, how do you acquire specialized skills? Conventionally, we go through an MTech program or a 3 years MS by research, or or a dual degree where it's BTech plus MTech, and then it's only suitable for a top university country. Or you could do advanced programs where you could start early, and this is something that gives them significant early more advantage, and it's more like a compressed master's curriculum into one in 1 year, right, and much lower cost than doing an MS abroad. So this is one program that we have. It's the IIT Bhubaneswar PG Diploma program. The details are on the website. I'll skip through this, but I want to focus on the advanced VLSI for a minute. Yeah. So these are the programs that we're running from Mossad Labs. We have an advanced VLSI chip design program, which is a 10-month program. And we focus on the two niche and the fundamental core skills even in VLSI, the analog IC design and the digital IC design. So this is where you learn really about how do you design ICs, how do you miniaturize ICs, how do you build sensors, how do you build the front end power management and so on. Similarly, on the digital design, we also run a postgraduate diploma in semiconductor technology and chip design. This is in collaboration with IIT Bhubaneswar. And then we have what is called as a MOOCs, or an NPTEL type of a course called Zero to Silicon. It is focused on foundational circuit analysis, basic circuit analysis, where we have seen students getting into trouble when you have two resistors they're able to solve, but if you put two resistors and one diode, right, that circuit somehow they get confused. Simplest of the circuits, but somehow fundamentally the analysis of how do you analyze circuits, RC circuits, RLC circuits, intuitively how do you understand this, right? These are important concepts if you want to do advanced analog design. Some of these concepts, fundamental concepts, are a collection of them have been taught as these video lectures. This can be taken as one course or an elective in students starting from second year onwards. So about advanced VLSI chip design program, this is a Mossad Labs initiative where you have 2.5 months of foundation course. So here we teach both analog IC design and digital IC design, and then the student gets to do a 1-month mini project where we give exposure to the EDA tools, because it's important that they learn the tool properly. How do you create a verification test bench? What simulations are needed to run? What are the requirements? How do you translate the requirements into a verification test bench? All of this general awareness about using the EDA tools is focused on the mini project. In that, the student can pick one of the specializations, like analog design or digital design. They will do this mini project there. Once they finish the mini project, they do a specialization course, which is an advanced analog design or advanced digital IC design. And through the specialization course, they start looking into feasibility study and come up with an idea for an IP design. And then they do a 4-month of internship where they are actually building that IP. So the outcome of this is every student who does this program should have designed